Okay, so with that, let's continue discrete math. We barely touched into it last time, but now let's jump into the substance of it. Now, why are we studying discrete math? Ultimately, why am I teaching this to you? I told you the heart of it. The heart of it is to teach you how to construct proofs. That's the heart of it. That's how you demonstrate understanding of some material, is you're able to prove it. That's what it means to understand. We already went over last time, prove 2 plus 2 equals 4 to me. And you guys don't have a clue where to begin. In fact, I asked you what's the definition of 4. And you don't have a clue where to begin except for someone who's actually learned arithmetic from you before. And it's not that it's hard. This isn't tricky to prove. And we'll prove that in this class just to give you a taste for it. The point is, you're told these things, you get comfortable with these things, but you don't really understand what it is that these things are. Grab an eraser, because a chalkboard eraser smears chalk more than it cleans chalk. So, part of this class is going to be proving, but really what I'm trying to get you competent in is what are called axiomatic systems. That's really what we're after, is trying to get you comfortable with understanding axiomatic systems. Every single theoretical body of knowledge, to the extent that it is a body of knowledge, is an axiomatic system or is composed of axiomatic systems. There's 4 components in every axiomatic system. There's what we call the axioms. These are our initial assumptions about some system. These aren't things we prove, they're just some initial statements. I'm going to set up a really simple axiomatic system. Our first axiom is going to be A1, all men are mortal. I'm going to set up axiom 2, Socrates is a man. It's a real stupid axiomatic system, but there we go. There's 2 axioms. All men are mortal and Socrates is a man. That would be an example of axioms. Now we have undefined terms. Every system has to have what we call undefined terms. You cannot define everything. It's impossible. Imagine I wanted to teach you French, and so I gave you a French dictionary. And so you open the dictionary and you want to learn your first French word. And so you look up some French word in the dictionary, and what does it give you?
French words.
A bunch of other French words. And you say, oh, I want to know what all those French words mean. And so you go and you look them up. And what does it give you?
More French words.
More French words. And you keep looking up and you get more and more French words, more French words, more French words. And so one of 2 things happen. Either your dictionary is ultimately circular, which our dictionaries are. Eventually you'll be back to a word that you were looking up. Or I gave you an infinite dictionary, and there's an infinite number of terms. Right? So we have to start out with some undefined terms. Terms that get their meaning from the axioms. Now, I could take this statement, all men are mortal, Socrates is a man. I could have rephrased this as all A's, well, all A are B. C is an A, whatever that means. Now, in this system, A, B, and C are undefined terms. What are they? I don't know. Undefined terms. They don't have a definition. And these axioms are somehow giving them meaning. I don't know what A is, I don't know what B is, I don't know what C is. But what do I know? I know whatever A is, all A's are B's. And I know whatever C is, it's an A. And that's what I know about. So the axioms just give us the basic information we know about our undefined terms, and then we construct definitions from our undefined terms. And we'll see examples of that. And then finally, so we'll construct definitions from our undefined terms, and then once you define a word, you can use it again to define new words, and define new words, and define new words. So we'll create a bunch of definitions, but the heart of mathematics, the heart of every axiomatic system, is all the theorems, all the proofs in that system. Now in our stupid system over here, there's really only one thing we can conclude. If all A are B and C is an A, what do we know?
C is a B.
C is a B. You just proved the theorem. We would call that theorem 1 in our axiomatic system. C is a B. If we were doing Euclidean geometry, Euclid has 5 postulates, 5 axioms. And you combine those axioms together to prove a theorem. And so taking axiom 1 and axiom 2, you might take those 2 together and prove your first theorem in Euclidean geometry. And then with that theorem in axiom 3, you might take those 2 together and prove some new statement, some new theorem. And Euclid, he only has 5 axioms, 5 postulates. Postulate, axiom, same thing. And from that, he proves all of geometry. every theorem in geometry follows just from those 5 statements. It's amazing. So you don't need a ton of axioms to get an extremely complex system. So that's the heart. All bodies of knowledge, they are these axiomatic systems. If I was teaching you Newtonian mechanics, our axioms would be Newton's laws of motion. That's what it means to be a law in science. You're in some sense an axiom in that field. So, trying to get you comfortable with these things. Same thing I was trying to do in geometry. Once again, discrete math, different medium, trying to teach you the same skills. For those of you who did geometry with me. Okay, and we already kind of talked about this a little bit. We'll talk about it one more time. So now, today, what I'm going to be starting with is teaching you logic. Why are we starting with logic? Logic underlies all of mathematics. So if I were to draw some pyramid here, I'm going to have to draw logic kind of big. But here's logic. I wrote its name to the side for a reason. We'll get to it. And then all math is built on top of logic. And then all science is built on top of math. And you can build history here on top of science if you want. What do I mean by that? That it's built on top of. I mean that you use logic to do math. You do not use math to do logic. You use math to do science. You do not use science to do math. That's backwards thinking. You use the math to do your science. You don't go out there in science and come up with some shocking result and say, math must be wrong. If you are a farmer and you see one hen laid 10 eggs and another hen, you count it and they laid 10 eggs, but then when you count it all together, you only count 19. You don't say, math must be wrong, 10 plus 10 is 19. You say, no, I counted wrong. The science must be wrong. Math is never wrong. You messed up, not the math. And so today, we're first going to rush through logic. To hurry up and give you your foundations for math, we're in a math course, but we're going to do a rush through of logic. Now logic is roughly split up into 3 pieces. We have what we call propositional logic, we have what we call predicate logic, and then we have what we call logic with identity, the equal sign. So first, we're going to go through propositional logic, then predicate logic, then logic with identity, and we're going to build up, and then we're going to start math next week. We'll also finish this last week and start math next week as well. So that's what we're roughly going to go through here. First, I'm going to start with propositional logic, the most basic of basic fields. We're going to presuppose that you know nothing except for some language that I can communicate with you in, namely English. Outside of that, presupposes nothing, so it's a nice, fresh start course. You don't have to know anything walking in these doors. Everything you're going to have to know for this course will be covered in this course. Any questions so far? All right. With that, let's jump into it. Propositional logic. For the purposes of this class, proposition, statement, same thing. So, our first definition, a statement. What is a statement? A statement is a sentence that is either true or false, but not both. What's a statement? Some sentence, some English sentence that you know and love, that's either true or false, but not both. We typically use Greek letters like alpha and beta to represent statements. So, which of the following of these is a statement? Tell me if it's a statement, yes or no. Go back home. No. You guys won't be told what to do. Not a statement.
Yes, that's a statement.
2 times 2 equals 5. Yes. 2 times 2 equals 4.
Yes.
Yes. New York is a suburb of Los Angeles.
Yes.
Yes, it is. Right? New York is a suburb of Los Angeles.
No, it's not.
It's a statement. It's a false statement, but still a statement. Right? Thursday up tar paper. No, it's a bunch of nonsense. Doesn't mean anything. The silliness is speedily. Nonsense again. I am the most beautiful girl in town.
Yes.
Thank you. This statement is false.
Yeah. Yes.
No. This is a tricky one. I'll never give you something this tricky on your homework. But let's think this one through for a second. This statement is false. So if it's a statement, it has to be true or false.
False.
Which is it? Is this statement true?
It's not a statement.
If the statement is true, but what does the statement say? This statement is false. So if it's true, then it's true that it's false. So it can't be true, so it must be false. So this statement is false. So then it's true. So if it's false, it's true. If it's true, then it's false. What is it? True or false?
It's not a statement.
Neither. So it's not a statement. What is a statement? A statement is a sentence that is either true or false, not both. So there's a tricky one. Try one more tricky one. X plus 2 equals 5. Is that a statement? We got some yeses, we got some no's. We got people still thinking. What do you think?
I don't think it's a statement.
Why not?
Because X can be anything as an undefined term.
Because X is a variable here. If X is 3, then it's true. If X is 2, then it's false. So is it true or false?
It's not.
Bad question. It has a variable in there that we need to fill in first. So this is an example of what we call a predicate. I erased my pyramid. So we'll deal with predicates after propositions. So first example of a predicate, we're not interested in those yet, just propositions. Remember, I mistake proposition over and over again. Statement, proposition, same thing. To be a little pedantic, technically a statement encodes a proposition. Okay, but now forget I ever said that. Statement, proposition, same thing. I may call it proposition because everyone calls it propositional logic. They don't call it statement logic. So, don't let me confuse you with those words. Okay, now we're going to introduce something that sounds a bit fancy, but it's really simple. It's called a sentential connective. All right, what is a sentential connective? These are the terms or phrases that can be connected onto sentences in a meaningful way. It's pretty vague what exactly this means. You take a sentence, throw some words or phrases on it. If the result is still meaningful, it still means something, it's not complete nonsense, then that was a sentential connective. There are infinitely many sentential connectives. Let's go through some examples of valid sentential connectives. Pretty hard to mess this up. Not is a sentential connective. I say all men are mortal. There's a statement that makes sense. I say not all men are mortal. I added it onto that statement and it still made sense. So it's a sentential connective. And, sentential connective. I can and two sentences together and the result still is meaningful. Or, Jack believes. It is probably the case that something, if one statement, then another statement. Some statement, if and only if, some other statement. Now, what are some examples of things that aren't sentential connectives? Cow the yesterday. The up pigeon too. Things that turn your sentences into nonsense. So it's pretty vague here. Sentential connective sounds complex, but it's pretty simple and pretty imprecise what exactly it means. But pretty intuitive what it means. So let's go through some examples. Let alpha be the sky is green. Now, let alpha be the statement the sky is green. So if I know that alpha is a statement, what do I instantly know about alpha?
Either true or false.
It's either true or false. It has to be one of those two things. In this case, it happens to be a false statement. Because the sky is not green. Double check. Okay, we're good. So, alpha happens to be a false statement. Okay. And we're going to let beta be 2 plus 2 is 4. Beta happens to be a true statement. Okay? Now let's look at some examples. The sky is green and 2 plus 2 equals 4. Is that meaningful?
Yeah.
Yeah. So, and is a valid sentential connective. The sky is green or 2 plus 2 equals 4. Is that meaningful?
Yeah.
Yeah. I didn't utter a complete nonsense. So it works. If the sky is green, then 2 plus 2 equals 4. You might say that's not a very good implication, but it's still perfectly meaningful. You understand what I'm saying. Jack believes the sky is green. Perfectly meaningful. So Jack believes is just a sentential connective. It is probably the case that 2 plus 2 is 4. Perfectly meaningful. Cal the yesterday, 2 plus 2 equals 4. Nonsense. So Cal the yesterday is not a valid sentential connective. Very vague what a sentential connective is. What is it? It's the terms or, not, I guess kind of vague. Imprecise. The terms or phrases that can be connected onto sentences in meaningful ways. That's a sentential connective. Good? Okay. So in logic, we are going to be interested in sentential connectives. In particular, there's only 5 that we're really interested in. I told you that there's basically infinitely many. It turns out there's only 5 we really care about. So we're going to study those 5 sentential connectives that really matter to us. Okay? Just 5. Nice and simple. So we can use sentential connectives to construct new statements by combining existing statements together. I can take New York is a suburb of Los Angeles. I can take I'm the most beautiful girl in town, and I can and the two of them together and functioning as our sentential connector. Okay, so introduce you to our third definition now. Conjunction. If alpha and beta are statements, what do I know about alpha?
Either true or false.
It's either true or false. What do I know about beta? It's either true or false. If alpha and beta are statements, the statement, alpha and beta, is called the conjunction of alpha and beta. So I told you there's only 5 sentential connectors we really care about, and is going to be one. So here's the first one we come across. There's only 5. Now, for those of you who have done this before, why should I take issue with this definition? If alpha and beta are statements, the statement alpha and beta is called the conjunction of alpha and beta. Why should I take issue with that definition?
Because the statement alpha and beta has undefined terms.
How do I know alpha and beta is a statement? I know alpha is a statement. I know beta is a statement. Just because you apply some sentential connective to it doesn't magically turn it into a statement, or it doesn't guarantee you it's a statement. I took a statement and I added on cow the yesterday. Well, that spit out a bunch of nonsense, right? How can I be sure that putting and between 2 statements, the result is still a statement?
You have to make sure it's true or false.
How can we guarantee that? And so we're going to define exactly what we mean by and here. And the symbol we're going to use for and is that wedge. You'll get used to it. So, how many of you have not seen a truth table before? So you've all seen truth tables. Okay, so I won't have to explain too much of what we're doing here. So, alpha and beta are statements. Which means, what are the 4 possible combinations I can have for alpha and beta?
True, true, true.
I can have alpha happens to be a true statement and beta happens to be a true statement. Here's one possible case. In that possible case, when we look at the statement alpha and beta, we need to check, is this in fact a statement? So I know alpha is true, I know beta is true. Is alpha and beta true or false? We better be able to call it one of those 2 things. Otherwise, we're lying and it's not a statement. Let me grab a marker and I guess some chalk. So we'll pretend alpha is a statement, Donnie's holding a red marker, and we'll pretend beta is a statement, Donnie's holding a piece of chalk. I said, so alpha is true and beta is true. Question, is it true that Donnie's holding a red marker and Donnie's holding a piece of chalk?
Yes.
Yes, that happened to be a true statement. And so, when alpha is true and beta is true, alpha and beta is true. Okay, what's another possible combination we could have for alpha and beta here?
True, false.
We could have alpha is true and beta is a false statement. Right? So let's set that scenario. Donnie's holding a red marker and Donnie's holding a piece of chalk. Is that true? Is it false?
Yes.
Yes, so we were able to call it either true or false. In this case, we happen to be able to call it false. What about when alpha is false and beta is true? Donnie's holding a red marker and Donnie's holding a piece of chalk.
False.
The result is false. And then finally, when they're both false, it's true, right? Donnie's holding a red marker and Donnie's holding a piece of chalk.
No, false.
False! Don't agree with me just because I say something. I talk a lot of nonsense. It's a big old false. But notice that no matter what, alpha and beta have to be one of these 4 things. They're statements. We covered every possible case for alpha and beta. And in every possible case, we were able to get a true or a false when we added them together. So if alpha is a statement and beta is a statement, then alpha and beta is a new statement. Something that we can always call true or false. Guaranteed. One of them. Make sense? Okay, so we just did and. Our first tricky one. Okay, now in logic, we love the word and. I told you that's going to be one of our special words, and. Let me give you an example of a word we do not like in logic. And that word is going to be the word but. What's the difference between the word and the word but? Let me give you an example. Some girl tells you, I love you, and I love your brother. What's she saying? She's saying that I love you is true, and she's saying that I love your brother is true. Right? Now, let's look at this one. I love you, but I love your brother. Do these 2 statements say the same thing?
Kind of.
No, not really. Yet, what is she saying here? When she says, I love you, but I love your brother, is she saying that she loves you? Yeah. Is she saying she loves your brother? Yeah. So logically, this says the same thing as this. It just says that's true and that's true. And yet we know that these are somehow saying something slightly different. There's something ambiguous about this word but. We can perfectly define exactly what we mean with and with the truth table. If I were to ask 100 different people what their definition of this word but is, I'd probably get 100 different versions. This is an ambiguous word. We don't want any ambiguity in logic. This is a good word for a poem. In a poem, you want to open your words up to many interpretations. In logic and in math, we don't want to be open to interpretation. We speak precisely, we say exactly what we mean. So but is a terrible word to use in logic, great word for poem. And is a great word for logic, bad word for a poem. Unless in your poem you don't want to be open to interpretation. Okay, so there's our first of our 5 special words. Good? Okay, so in logic, we are only interested in the univocal parts of language. Uni meaning one, univocal, one interpretation. Not multiple interpretations, not ambiguous, univocal. There's one and only one interpretation. Everyone can agree on what exactly that word means. Those are the words we like. Those are the words we love. Those are the words we'll use. Okay. I gave you an example of a sentential connective that we love here. Now, the sentential connectives that we love in logic are going to be what we call truth functional sentential connectives. This is going to be a mouthful, but the concept, pretty easy once you get it. So truth functional sentential connectives, what are these? These are sentential connectives where the truth or falsity of the resulting statement can be completely determined from the truth or falsity of the component statements. We'll go through some examples, then I'll read that definition again, and I think it'll click. So I know that's a lot to take in. Let's do some examples. So let alpha and beta be any 2 statements. So what do I know about alpha and beta?
They're either true or false.
They're either true or false, whatever they are. Right? We'll just randomly pick. So we have alpha be, I don't know, the sky's blue. So there's our alpha. Beta, what should we have be? Something like 2 plus 2 equals 5. So alpha happens to be a true statement. Beta happens to be a false statement, just as an example. But all we know about them is it's for sure either true or false, and that's for sure either true or false. Okay? Now, which of the following connectives are truth functional? Truth functional means we can completely determine the truth or falsity of the resulting statement if we know the truth or falsity of its component statement. So we have alpha is the sky is blue. Question, true or false? Jack believes the sky is blue. Is that true or is it false? Let's have our truth table really quick here. So we've got alpha. Alpha, whatever is either a true or a false statement. Jack believes, let me make up a symbol for it. We'll do J and B hooked together for Jack believes alpha. Jack believes alpha. So alpha happens to be a true statement, like the sky is blue. Question, Jack believes the sky is blue. Is that true or false?
It's
It's true, he believes it.
true. You gotta ask it. No.
How do you know he believes it?
That's what it means.
Well, you're wondering, is it true that Jack believes the sky is blue? So you know the sky is blue. Question, does Jack believe the sky is blue? How on earth can you know whether or not Jack believes the sky is blue?
Yeah.
Let's say I'm Jack. You can even ask me, hey Jack, is the sky blue? I say no. Do I believe the sky is blue? Maybe I'm just lying to you. There is no way for you to determine whether or not Jack believes the sky is blue. So this is not a truth functional sentential connective. It is a sentential connective. The statement, Jack believes the sky is blue, makes perfect sense. It's perfectly meaningful. But it's not something you can call true or false. A connective, a sentential connective, is truth functional if and only if you can determine the truth or falsity of the resulting statement by knowing the truth or falsity of the component statement. The only way that this can be truth functional is if every time I tell you alpha, whether it's true or false, you can determine whether this whole thing is true or false. But you can't do that. If I give you a true statement here, you can't determine if this is true or false. If I give you a false statement here, you can't determine if this is true or false. So it's not truth functional. Let's try another one. it is not true that alpha. So we'll say alpha, we'll start out with the true statement, the sky is blue. It is not true that, I may come up with a symbol for that, got to make one up off the top of my head. I'm going to just do a line over with a deep down like that. And that stands for it is not the case. That. Good? So, if, let's pick alpha to be a true statement, the sky is blue. True or false? It is not true that the sky is blue. That's a false statement. So when I gave you a true statement, you were able to determine if this is true or false. Now, let me give you a false statement. It is not true that 2 plus 2 equals 5. True. So when I gave you a false statement, you were able to, when I gave you a true statement, you were able to determine if this was true or false. And when I gave you a false statement, you were able to determine whether or not this was true or false. So this is a valid sentential connective, it's a valid truth functional sentential connective. Let's read truth functional now. We've done a couple more examples and see if the definition sinks in now. What does it mean to be a truth functional sentential connective? It's a sentential connective where the truth or falsity of the resulting statement can be completely determined from knowing the truth or falsity of the component statements. Good? Okay. Let's try another one. Alpha and beta. Is and here truth functional?
Yes.
If I know alpha is true and beta is true, then alpha and beta is true. What if alpha is true and beta is false?
False.
What if alpha is false and beta is true?
False.
What if alpha is false and beta is false?
False.
We handled all the possible scenarios. And in every possible scenario, you were able to determine if this thing was true or false. So and is a truth functional sentential connective. It's one where you can determine the truth or falsity of the entire statement if you know the truth or falsity of its component statements. Is this starting to make sense? Okay. Let's do one more. It is probable that beta. Is this one truth functional? So we'll put beta here. Beta can either be true or false. We'll make up some symbol for probable. We'll do a loopy. Okay, it is probable that beta. If I know that beta is true, let's say beta happens to be a true statement. Is it probable that beta? What do you think?
No. Well, it's not.
Is there a way to determine if it's true or false?
No.
Let's pretend beta is a statement, I'm wearing shoes. Is it probable that I'm wearing shoes?
Yeah.
Yeah, in that case, it happens to be probable. Let's say that it was a case that I just won the lottery. And beta is a statement, Donnie won the lottery. So it's a true statement. Is it probable that I won the lottery?
No.
No, in that case, it's false. So some true statements here make the result true, and some true statements here make the result false. And so just by knowing whether or not beta is true is not enough to determine if the whole thing is true. You have to actually know which statement beta is. Make sense?
Yeah.
So it is probable that is not a truth functional sentential connective. Perfectly fine sentential connective, but not a truth functional sentential connective. So in logic, not only are we interested in sentential connectives, we're only interested in special kinds of sentential connectives. We're interested in truth functional sentential connectives that are completely univocal. No ambiguity about what the word means, like the word but. That's what we care about. And happens to be one of those words. Let's move on now to our second word. Disjunction, or. So if alpha and beta are statements, the statement alpha or beta is called the disjunction of alpha and beta. Now again, I called alpha or beta a statement, so we better be able to determine the truth or falsity of this thing simply by knowing whether or not alpha is true and whether or not beta is true. So or is going to be one of our special words here, or. Our special symbol for or is that. Flip the wedge over. And let's write out a truth table for it real quick. Because if it's a truth functional sentential connective, we better be able to draw a truth table for it. So I've got alpha here, I've got beta here, and now we're going to look at alpha or beta. Now, alpha and beta, what are the possible combinations we could have? Well, we could have alpha's false and beta's true. Right?
Yeah.
Let's think through that case. We'll set it up. Alpha will be Donnie's holding a red marker. Beta will be Donnie's holding a piece of chalk. So I'll set up that scenario. Donnie's holding a red marker, or Donnie's holding a piece of chalk. Is that true or false? It's true. I'm holding a red marker or a piece of chalk. So that is true. Okay, we could have had alpha true and beta false. Donnie's holding a red marker, or Donnie's holding a piece of chalk. Is that true?
Yep.
Okay. So we were able to call it true or false. We could do false, false here. Donnie's holding a red marker, or Donnie's holding a piece of chalk. False. I'm lying to you. If you can call me a liar, then it's false, right? And then finally, Donnie is holding a red marker, or Donnie's holding a piece of chalk.
Yep.
Is that true? Yes, it's true. Now, some of you might not like that one very much, and that would be perfectly natural because of the English language that we use. So, logic does not care about the English language. Logic comes way before the English language. Or is the word in the English language we choose to encode what is meant by or in logic. We have to pick some English word to capture this concept. We could do logic in Greek, and logic is still just logic. We could have done logic in Mandarin, and logic is still just logic. So we have to pick an English word to get this concept. Now, unfortunately, in English, we use or two ways. The first way we use it is called the inclusive or. An example of a statement using or in the inclusive or way would be if I said, you must take physics or calculus to apply for my class. And let's say you took both physics and calculus. Can you apply for my class?
Yes.
And so I mean this in the inclusive sense, where if both are true, I was counting that case. I was including it, the inclusive sense. On the other hand, the exclusive sense that we use or, when you go to a restaurant, they say, that order comes with a side of salad or soup. And you say, perfect, both. It's not what they meant. They meant one and not the other, or the other and not the one. They weren't including the case where you get to call true and true true here. So that's when we use it in the exclusive sense. And so sometimes, in logic, you can use the exclusive or. They call it XOR. And the symbol for that looks like this. And if we were doing our truth table here for XOR, alpha XOR beta, then it would be true, true, false, false here. It wasn't including the case where both alpha and beta were true as true. That's the way your waiter meant it. Now, exclusive or, it's a perfectly fine logical symbol. It's a perfectly fine truth functional sentential connective. We could include it in our logic if we wanted to. It's not one that we use very much. So that's not going to be one of our special 5. So we're not going to be covering every possible symbol we could use in our logic. We're just going to pick the 5 that are most frequently used. For those of you who have done this more often, how many binary operators could we have here? Sixteen different ways that you can fill out this.
Oh.
And so you come up with an operation for each of them. So there's technically 16 we could come up with in our logic for combining 2 together. We're only going to use 4 that combine 2 together and 1 that stands alone. Okay. So that was OR. And we talked about XOR. Okay. So, next, we'll talk about one that we've already touched upon a little bit in an example, negation. If alpha is a statement, the statement alpha is false is called the negation of alpha. We also say not alpha, or it is not the case that alpha. Those are all logically equivalent. Now, once again, I'm calling that statement, so we better be able to come up with the truth table for it. So, alpha, oops, I already started special words. And is special, or is special, not is special. Its symbol was that, its symbol was that. This one's symbol is that. So, not alpha. Now, I told you alpha is a statement, so what do we know about alpha?
Either true or false.
It's either true or it's false. Okay. If alpha is a true statement, then not alpha is
False.
false. And if alpha is a false statement, not alpha is true. This one seems like it has the most straightforward definition. Harder to get easier than not, right? Pretty straightforward?
Yeah.
If alpha is true, not alpha is false. If alpha is false, not alpha is true. Make sense? It's just saying the opposite of it. It's just saying whatever the other one is, it's just saying the other one's false. Let's give an example. Let's say alpha happens to be the statement 2 plus 2 is 4. I say 2 plus 2 is 4 is false. Was my statement true or false? False. So if alpha was true, not alpha is false. On the other hand, if alpha happens to be the statement 2 plus 2 is 5, and I say 2 plus 2 is 5 is false, then it's true. Good?
Yep.
Okay. And we write not alpha as that sign alpha. Okay. Now, this one is actually kind of tricky. Not alpha, the negation of alpha, is the contradiction of alpha. If I know that alpha is true, not alpha has to be false. And if I know that not alpha is true, alpha has to be false. They have to be able to be paired up this way. Alpha and not alpha are always contradictions of each other. When you have two contradictory statements, one of them has to be true and one of them has to be false. If I give you alpha and not alpha, one of them has to be true and one of them has to be false. And I seem like I'm overstressing this. Let's do some examples. Those of you who have done this before, you don't get to do this one. Which of the following are negations of our alpha here? Here's our statement alpha. All swans are white. There's alpha. We are trying to figure out which of these statements say not alpha. Which of these statements are the contradiction of this statement? And it could show up multiple times in just different words. Okay? So, all swans are white, there's our alpha. Some swans are black. That contradicts this, right? So this is not alpha. No, your initial instinct was right. This and this are not contradictions of each other. How do I know they're not contradictions of each other? Remember, if they're contradictions, then anytime this is true, this has to be false. And anytime this is true, this has to be false. If they're contradictions of each other. If alpha is true, not alpha has to be false. And if alpha is false, not alpha has to be true. So let's say that we lived in a universe of all yellow swans. Question, are all swans white? No. Okay, so some swans are black. No, you can't say that. So this is not the contradiction of this statement. This is not the negation of this statement. Let's try another one. All swans are white? No swans are white. Okay, there's a contradiction, right? We got one thinking about it. She's saying yes. Okay, you're all saying yes. And you're all wrong. Let's set up the universe. Half our swans are white, half are black. Are all swans white? No. Oh, so no swans are white? No, half are white and half are black. They're only contradictions of each other. If in every possible scenario, every possible case, no matter what it is, anytime this is true, this has to be false, and anytime this is true, this has to be false. Very subtle. Don't worry, these guys all screwed up just like you did when they did it for the first time. Okay, let's try another one. Now we got you thinking. Don't worry, none of these are. Except this one. I wouldn't give you 3 wrong in a row, right? Okay. All swans are white, some swans are not white. Is that the contradiction? All swans are white, some swans are not white. Okay, we got you thinking. Fantastic. Let's check. Let's say we live in a universe where all swans are white. Is this true? Yeah. And is this false?
I mean, yes.
We live in a universe where all swans are white. So, are all swans white?
Yes.
Yes. Are some swans not white? No. So when this was true, this was false. Okay, so far we're good. Let's say we live in a universe of all black swans. Are all swans white? No. Are some swans not white?
Yes.
Yes. So when that one was false, that was true. Okay. Let's say we live in a universe of halvesies. Half are white, half are black. Are all swans white? Are some swans not white? So it works. These two are contradictions of each other. And here's how to try and think about it. If I say all swans are white, and you call me a liar, so I say all swans are white, and you scream, liar! What are you saying? You are saying some swans are not white. That's what it means when you call me a liar. You're stating the negation. You're stating the contradiction. So either all swans are white, or some swans are not white. Has to be one of those two cases. So this one, yes, is a negation of that statement. Tricky, tricky. All right, let's try the next one. I couldn't give you two right ones in a row. All swans are white. Not all swans are white. Either all swans are white, or not all swans are white. That's the most straightforward negation of it. Right? When you not something, it gives you the negation. So either all swans are white, or not all swans are white. Has to be one of those two cases. Anytime you're doing your algebra test and your teacher tells you to solve for x, you can always say x equals 6 or x does not equal 6. It's always one of those two. Either x is equal to 6 or it's not equal to 6. Guaranteed, teacher. Doesn't matter the problem. Right? They contradict each other. It's either alpha or it's not alpha. Has to be one of the two. Ace it. Just taught you how to get a perfect score on every test. Okay. Let's try one more. All swans are white. Every swan is not white. Are those contradictions? All swans are white. Every swan is not white. What do you think? Torn? All swans are white. Every swan is not white. Let's set up a universe. Let's say we live in a universe of half white, half black swans. Are all swans white? No. So is every swan not white? If they're half black, half white. No. So these ones are not contradictions of each other. So if you can come up with a single case where they're not negating each other, if you can come up with some universe where you're not guaranteed one's true and one's false, then they can't be negations of each other. Has to be one or the other. Okay. So negation. Very subtle, very tricky. Hard to get the first time through. Okay, so that covers not. Now we move on to, time we're at? Almost done, okay. Now we move on to, just some examples. So now we're just going to state the negation of each of these statements. So now we're going to be coming up with the negation rather than just trying to select it from some list. Okay? This is what your homework is going to be for the first week, stuff like this. This is exactly one of your homework problems. Okay, so let's try it out. All men in Georgia are at least 6 feet tall. We're looking for the negation.
Some men in Georgia are not 6 feet tall.
All men in Georgia are at least 6 feet tall. What would be the negation of that? How could you prove the statement false?
You can find an example where one is not 6 feet tall.
Yeah, if you can find one guy in Georgia who is not at least 6 feet tall, then you prove the statement's false.
Yeah.
If I say all men in Georgia are at least 6 feet tall, and you scream liar at me, what are you saying? You're saying that there's someone in Georgia who is not at least 6 feet tall. So the negation of this is rather than saying all men, you say some men in Georgia are not. The not going right here.
Yeah.
Are not at least 6 feet tall. That's the negation of this statement. You could have also been very lazy and said, not all men in Georgia are at least 6 feet tall. That's the lazy way to do it. Don't do it that way on your homework. When I tell you to negate it, I do not mean put a not in front of it. All right, let's try another one. All students in France like geometry. Liar! What are you saying if you're calling me a liar? Some students in France.
Do not like geometry.
Some students in France do not like geometry. Perfect. Let's try another one. Every rectangle is a square.
Some rectangles are not squares.
Some rectangles are not squares. Call me a liar. What are you saying? Every circle has a center. Liar. What are you saying? Some circles are missing centers. Some circles do not have a center. There's a circle in existence with no center. That's what would be you'd be asserting if you call me a liar. Let's try a trickier one. Not geometry students. For every pair of numbers A and B, A plus B equals B plus A. Okay, that's a difficult one. For every pair of numbers A and B, A plus B equals B plus A. I say that. For every pair of numbers A and B, A plus B equals B plus A. You say, you liar! What are you saying?
For some pair of numbers,
For-
A plus B does not.
Perfect. For some pair of numbers out there in existence, A and B, A plus B, we'll just say is not equal to B plus A. Just find some pair of numbers where this isn't the case and you prove me wrong. That's what you mean when you call me a liar. Some men play golf.
All men.
All men play golf?
All men do not play golf.
All men.
I say some men play golf, you say you liar. All men play golf. Doesn't work. All men do not play golf. And you'll notice this pattern that we keep doing over and over again. When there's an all, we replace it with like a some and then somehow stuck a not in there. And when there was a some, we somehow replace it with an all and stick a not in there. Now there's also a way that we can do it with no word. This is a perfectly acceptable one. You could have also said, no men play golf. No men play golf is saying the same thing as not, or all men do not play golf.
Yeah.
No men play golf, all men do not play golf.
Okay.
Whole exercise, and I don't know if I stress this point enough. Why are we doing all this? Why am I going to make you do a bunch of these statements? I need you to be able to read English and know exactly what it's saying. Precisely. So that's the point of all these exercises. And so you should be able to take an English statement and state its opposite. That's a good thing to know how to do. If you're going to call someone a liar, what exactly are you asserting? Because you guys go around calling people liars all the time, right?
Yeah.
So what are you even saying? Let's figure out what you're saying. Okay. There is at least one number x such that x plus 3 equals 7. You liar.
For every number x.
Yeah, there is at least one. Like the cross-out version of that is for all numbers x, right? This is a weird way of saying some. There is at least one is the same thing as some. Is someone in that room? It's true if there's at least one person in the room. So some means at least one.
There is no.
So when we do it, we get rid of the some and somehow do it with an all. So there's at least one number, means that we're going to do this for all numbers. So this is going to be for all numbers x. X plus 3 is not equal to 7. So if I say there's at least one number x such that x plus 3 equals 7, and you call me a liar, you're saying for any number x, x plus 3 is not equal to 7. You cannot find one that satisfies it. It is never the case. So x plus 3 is never equal to 7. Make sense? Okay. So, some good exercises negating. Let's do some more negating. Get trickier when we throw that and word in there. Keep erasing the top. All our special words. And, or, no. Okay. So for those of you who did not do geometry, we're going to now try and negate a conjunction. So notice we have a statement here, and we have a statement here. So think about that as like your alpha, that is like your beta. Okay, today is Monday, and the weather is cold. Liar. What are you saying when you call me a liar? So what are you asserting? Tell me the statement you must be asserting. If you're saying I'm a liar, what are you saying?
It is not Monday or the weather.
You're saying today is not. Today is not Monday.
Weather is cold or weather is not cold. I don't know.
And the weather is not cold. Is that what you said?
Yeah.
Yeah. Sounds certain. Not. So let's see, is that the opposite? So today is Monday and the weather is cold. You say liar. You must be saying that today is not Monday and the weather is not cold, right? Let's pretend that the weather's warm and today's Monday. Okay? Is it true that today's Monday and the weather is cold? No. Oh, so is it true that today is not Monday and the weather is not cold? No, it's still Monday. So what are you saying?
And the weather is not cold.
You're saying what?
It is Monday and the weather is not cold.
So you want to do it like this?
Yeah.
Okay. No, she sees the problem. It's not working. We're stuck. So let's draw our truth table for alpha and beta really quick. So sorry, I should have done alpha here, beta here. We could have true, 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 false, false, true, false, false. True and true is?
True.
True and false is?
False.
False and true is?
False.
False and false is?
False.
So we need our negation that we write here to be true whenever alpha and beta is false. So when is alpha and beta false?
If one of them is false.
If alpha is false or beta is false. So if we have not alpha or not beta, then we have not alpha and beta. So today is not Monday or the weather is not cold. You're so close. Make sense?
Yep.
And now that's the negation. Either today's Monday and the weather is cold, or it's going to be the case that today's not Monday or the weather's not cold. One of those two have to be the case. Either it's Monday with cold weather, or it's the new statement. It's either not Monday or it's not cold weather. Make sense? Has to be one of those two. Okay, and what we just barely showed is that when you negate alpha and beta, when you try and negate alpha and beta, the negation of this is just false, true, 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 right? Just negated this column. And what we just barely showed is not alpha and beta is the same thing as not alpha or not beta. Let's just see this in truth table form. So we're going to do not alpha or not beta. If alpha is true, not alpha is
False.
false. If beta is true, not beta is false. False or false is false. I'm holding a red marker or I'm holding a piece of chalk. False. False or false is false. Okay, let's set up this scenario. If alpha is true and beta is false, then not alpha is false and not beta is true. False or true is false or true is
Oh.
I'm holding a red marker or I'm holding a piece of chalk. True. False or true is true. Okay, next one. Alpha is false, beta is true. So we have true or false is true. And then finally, if alpha is false and beta is false, then not alpha is true, not beta is true. So true or true is true. And now notice, shockingly, not alpha or not beta is the same thing as not alpha and beta. They're identical. That means they're logically equivalent. Do you know how I got this column? I was just negating this column.
Yes.
So here's alpha and beta. So here's not alpha and beta. I just replace truths with falses and falses with truths. And it turns out this also gives you the exact same thing as not alpha or beta. Or sorry, as not alpha and beta. When we negated today is Monday and the weather is cold, we got today is not Monday, not alpha. We replace our and with an or, and the weather is not cold. So the way that we say that is when you distribute a not, it converts ands into ors. That's how you distribute a not. Make sense? Good? Okay. Negating a disjunction. Let's do that. So this time we're negating an or statement. Oh, we didn't go through all the examples on the other side. We'll do all the examples on this side. Okay. I say, I will study or I will fail. You call me a liar. What are you saying? Let's twist it around. I tell you, you will study hard or you will fail. And you call me a liar. What are you telling me you're going to do?
I will not study hard and I will pass.
You're saying that you will not study hard and you will not fail. So I say, you will study hard or you will fail. You say, watch me. I will not study hard and I will still not fail. So when you not a disjunction, you replace it with an and to distribute your not in. So let's do this one with the truth table. Replace our and here with an or. We'll negate alpha or beta, and then we'll look at our resulting statement over here. So we gotta replace these. Okay. So alpha and beta, two statements. Here's all their possible four combinations. True, 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 false, false, true, false, false. True or true is?
True.
You guys just gonna go with that? Okay. True or false is? False or true is? And when they're both the same, it's? In this case. Okay. Now let's negate it. Not true is? Not true is? Not true is? Not false is? Okay. Now, over here, what this is hinting at is that we should write not alpha and not beta and get the same thing. So let's check that just by thinking it through from here. So, if alpha is true and beta is true, not alpha is false and not beta is false. So false and false is false. If alpha is true and beta is false, not alpha is going to be false and not beta is going to be true. False and true is? False and true is? False and true is? Repeating isn't an argument. Don't change your position just because I repeat. You are correct. It is false. Okay. Now let's have our next scenario. If alpha is false, not alpha is true. If beta is true, not beta is false. True and false is? False. Wonderful. And then finally, if alpha is false and beta is false, then not alpha is true, not beta is true. True and true is? True. And look at that. We got the exact same thing. They're logically equivalent. So when you distribute a not over an or, it converts it into ands. There's another way to remember that. Okay. Now this time, let's finish out stating the negation of each of our examples. So, some will work, or all will starve. We're coming up with the negation. Some will work, or all will starve.
Some will not work, and all will not starve.
Let's think that through for a second. So you're saying some will not work. What? And all will not starve?
Yeah.
Let's think that through. I tell you some will work or all will starve. And you say, liar. What are you saying? What's the opposite of some will work? I say, are some people work on that job site? And you tell me no. What are you telling me?
There's no one there.
No one's working. So the opposite of some will work is none will work. Not some will not work. Because that could have also already been true with some working. Could have had some working and some not working. So remember, you got to negate each individual statement. So what's the negation of some will work?
All not work.
All will not work, or none will work. However you want to say it. For the sake of convenience, I'm going to write none. So none will work, and what's the opposite of all will starve?
Some will not starve.
Some will not starve. Some will not starve, right? You can have a sick little colony of cannibals, right? Where nobody works and at least one guy survives. Okay. Every triangle is isosceles, or every triangle is right. We got to negate, replace our or with an and then negate again. So what's the negation of every triangle is isosceles? Yeah. Some triangles is not. We're going to have fun with the English. Some triangles is not isosceles. Or some triangles is not right. Some triangles are not isosceles or some triangles are not right. Don't use that bad English on your homework. Okay. No roses are red, or some violets are blue.
Some roses are red.
Some roses are red, and not all violets are blue, or no violets are blue.
Same thing.
No violets are blue. What's the opposite of some violets are blue? I say, are some violets blue? And you say no. You're saying no violets are blue.
Yes. No, yes.
It'll trick you up, and then you'll get it, and then it'll trick you up again. Okay. And so what we were showing is that not alpha or beta is the same thing as not alpha and not beta, which is what we showed on the truth table diagrams.
Yeah.
Okay. Now another example of words that we care about in English. We like the word not. We don't use the word never. So I'll give you another example of a type of word that we don't want in logic. Never, terrible word for logic. Let's look at it. The sky is not blue. What is this saying? This is saying the sky is blue is false. The sky is not blue. That's what it's saying.
Yeah.
The sky is never blue. What's that saying? It's saying the statement, the sky is blue, is false. But do they say the same thing? No, they both kind of say that the sky is blue is false, but they're still somehow different. Never is somehow trying to bring into this weird component of physics and time into the picture, as though change is something. We're not interested in physics here in this math. Physics is a science. We're still in just a brute force math. So we won't use a word like never. We'll use a word like not. Okay. So we've covered 3 of our special symbols. Before we get to our 4th special symbol, and the hardest of our special symbols, it's going to be the one that we often relate with proofs. So let's talk a little bit about proofs. When we prove something. So when you try to convince someone of the validity of some statement, you get in an argument with someone, you tell them that this is true because that is true. It's usually phrased that way. How do you know this? Well, because of that. How do I know that Tom Brady is the greatest quarterback of all time? Well, because he has the most Super Bowls of all time. And so if you accept the person with the most Super Bowls is the greatest quarterback, then you have to accept that Tom Brady is the greatest quarterback. So if you accept the that, then you have to accept the this, if we can show that this necessarily follows from that. And so we're going to need a way of encoding that, which is what our next word is going to do. So if you agree that the that is true, and you agree that the this necessarily follows from the that, then you would be convinced by this argument. Now, proofs, always and forever. Every proof, every theorem. Remember, theorems is what math is 99% all about. Every proof, every theorem is in the form, if some statement, so-and-so, is true, then such and such must also be true. They're always stated as if something, then something. Give you an example. Your favorite theorem that you all know and love and have memorized was the Pythagorean theorem.
If you have a right triangle, then the legs of the triangle squared and added together is 10.
Now, odds are, if he wasn't there, you would have all told me what?
A squared plus b squared.
A squared plus b squared equals c squared. And people always say, here's the Pythagorean theorem. It makes me want to throw a piece of chalk at it. A squared plus b squared is not a theorem. It's just an equation. It's not even a universally true equation. If I tell you a is 1 and b is 2, c is 3, is 1 squared plus 2 squared equal 3 squared? No. What do you mean? A squared plus b squared equals c squared. What on God's green earth does that have to do with the Pythagorean theorem? What's the Pythagorean theorem? And so now, someone who didn't take geometry from me, what's the Pythagorean theorem? Come on. It's like the one theorem we can count on you knowing. You know it relates to, has something to do with what shape? Has something to do with triangles. Maybe a special type of triangle. A right triangle. She's mouthing words. So, a right triangle. The theorem says, if you have a right triangle where one leg has length A and one leg has length B and the hypotenuse has length C, then A squared plus B squared equals C squared. It says if you have this, then you have that equation. And it's phrased as an if-then statement. Every theorem is, or can be rephrased that way. So they're always saying if something's true, then something else is true. Because it always starts out with just our axioms. And then our first theorem says, well, if we have all men are mortal, and if we have Socrates as a man, then we have Socrates is mortal. And we go on our merry way. If then, if then, if then. All the way up, building up as we go, starting with our axioms. So every theorem can be phrased as an if-then statement or as an implication. You do proofs all the time in algebra, just nobody tells you you're doing a proof. They give you 3x equals 4, and they say solve for x. If 3x equals 4, then what does x equal? 4/3. You divide both sides by 3. That's a little proof. If 3x equals 4, then x is equal to 4/3. If a equals 2 and b equals 3, then a squared plus ab equals 10. 2 squared is 4. 2 times 3 is 6. 4 plus 6 is... There we go. Didn't like it. So all mathematical proofs are of the form, if some statement, then some other statement. In this form, we call alpha here the condition or the antecedent. And we call beta the conclusion. You will get very used to this language. You will hear me say antecedent 1,000 times throughout this class. Alpha is called the antecedent, beta is called the conclusion. If the antecedent is true, then the conclusion is true. So we call these, we call alpha the antecedent or the condition, we call beta the conclusion. Okay, so now we're ready to jump into our fourth special symbol, the implication symbol. So the fourth word that we care about is implies, and we represent it with an arrow. And we represent it with an arrow. Implication. If alpha and beta are statements, then the statement alpha implies beta is called an implication. Now we have a bunch of different ways of saying alpha implies beta. That's the same thing as saying if alpha then beta, beta if alpha, alpha only if beta, alpha is a sufficient condition for beta, and finally beta is a necessary condition for alpha. These all say if alpha then beta, or they all say alpha implies beta. Different ways in English of saying the exact same thing. And so we got to get comfortable in English, reading the English, and understanding what exactly it's saying. And notation, we write alpha implies beta as alpha over rho beta. So let's practice just with the English for a second before we get to our truth table. And just try reading the statement and understanding it. So we're going to put the following statements into an if alpha then beta form. This is going to be on your homework. If alpha then beta. So take this statement and rephrase it as an if alpha then beta. So I tell you, if I eat strawberries, I get hives. What am I saying?
If I eat strawberries, then I get hives.
I'm saying if I eat strawberries, then I get hives. I eat strawberries is my antecedent. I get hives is my conclusion. I know if I eat strawberries, then I get hives. What if I got hives? Do I know I ate strawberries? No, maybe I'm also allergic to something else. But what I know for sure is that if I eat strawberries, then I get hives. That's what the statement's saying. It's saying if this is true, then that is true. It is not saying if this is true, then this is true. The implication is going that way. This being true implies this is true. So we're always trying to identify which one's the antecedent, the condition, and which one's the conclusion. And then once you know the antecedent and the conclusion, you just write if, antecedent, then conclusion. So on this problem, you would literally write, if I eat strawberries, then I get hives. Nice and simple. Good? Let's try the next one. People who don't study mathematics don't have good sense. What's the antecedent? What is it saying? Is it saying if you don't study mathematics, you don't have good sense? Or is it saying if you don't have good sense, you don't study mathematics?
Saying if you don't study mathematics, then you don't.
Right, so it's saying if you don't study mathematics, then you don't have good sense. So if you don't study mathematics, you for sure don't have good sense. That's what this is saying. If I know you don't have good sense, does that mean you don't study mathematics? We can't conclude that from this. Maybe you study mathematics all the time, but you walk across the street with your eyes closed. You can still have bad sense and study mathematics. But if you don't study mathematics, you for sure don't have good sense. So the implication is going this way. Not studying implies not good sense. Next one. The crops will be saved if we have rain this week. Which one's the implication, or which one's the antecedent, which one's the conclusion?
If we have rain this week, then.
Perfect. We're saying if we have rain this week, then the crops will be saved. That's what it's saying. So it's saying if you were to actually write this out, you would write if we have rain this week, then the crops will be saved. That would be doing the homework assignment. That's how you would write it out. So we know if we have rain this week, then the crops will be saved. Do we know if the crops were saved, then we must have had rain? No, maybe the farmer paid to just barrel in tons of water. Who knows? Did something crazy to save the crops. But for sure, what the statement is saying is, if we have rain this week, then the crops will be saved. But the crops may be saved some other way. So it's saying, if we get the rain, then we got to save crops. It will rain tomorrow only if it gets cold. Is the rain implying the cold, or the cold implying the rain?
Cold implying the rain.
Cold's implying the rain? Rain implying the cold? Cold implying the rain? It will rain tomorrow only if it gets cold.
The rain implies the cold.
The rain implies the cold? The cold implies the rain?
And get cold without raining.
This is one of those ones where if I get you, I can get you to one way say it one way and one way say it the other way. This is the one that confuses the kids the most, when it's phrased only if. Now it turns out that it is saying the rain implies the cold. And I'll make this one appeal to your intuition because it comes up enough. I'll give it to you with just different words. So, there is oxygen if there is fire. Is that a true statement? There's oxygen if there's fire. That is a true statement. And which way does the implication go? Does fire imply oxygen or oxygen imply fire?
Fire.
Fire implies oxygen. If oxygen implied fire, we'd be in trouble. Right? We'd all be burning right now.
Yeah.
So, if there's fire, then there is oxygen. If does the implication this way. It's saying fire implies oxygen. Only if goes the other way. So, tell me whether or not the statement's true. There is fire only if there is oxygen. Is that statement true? Yes. And notice that we swap the sides that those are on. So if the implication goes from right to left, only if the implication goes from left to right. These both say the exact same thing. And notice how we swap the sides the statements are on. Good?
Can we go back up to the people who don't study mathematics? How would we write that one?
There's a bunch of different ways you can say it. You can say if someone doesn't study mathematics, then they don't have good sense.
Okay.
I'm not going to care too much about the English. I'm going to be scanning that you had if something about not good sense, then something about, if look for not mathematics, then not good sense. So I'll just be scanning at a high level for making sure you got the right idea on each side of the implication. Okay. Any other questions? The if and the only if, these are getting confusion. It's tough in a statement like this to quickly get it. It helps when you have one that already appeals to your intuition a lot, and then you can see it. So those you'll get caught up on a few times. Remember, if and only if point in opposite directions, and for whatever reason, if is more intuitive to our brain. And so just remember, only if is opposite of if, and that'll probably help. Goes the other way. Okay.
I love how we just implied for the next one.
We'll skip that one. You'll do it on your homework, but it's just switch around. Now let's do some proofs. So we're going to keep setting up really simple axiomatic systems here and construct some proofs. Ish. So we're setting up a system. Here's what we know in our entire system. If Fred is on the team, he must go to bed early. Okay? Take that for granted. If Fred's on the team, he must go to bed early. What can you conclude if Fred goes to bed early? If Fred's on the team, he must go to bed early. If he goes to bed early, he must be on the team, right? Wrong. Maybe he didn't make the team and he's depressed. So he went to bed early. He can go cry it out. On the other hand, so if Fred's on the team, he must go to bed early. I tell you, Fred does not go to bed early. He's for sure not on the team. Because if he was on the team, he must go to bed early. So if he doesn't go to bed early, you for sure conclude he's not on the team. Okay, try another one. Take it for granted. If a man is a postman, he has foot trouble. Okay, assume that's true. What can we conclude if we know that this man has perfect feet? He's not a postman. Because if he was a postman, he'd have foot trouble. What do we know if that man over there, Bob, he has foot trouble? He might be a postman, he still might not be a postman. Poor Bob gets stepped on now. Right? You will be given a ticket only if you are a sophomore. Gene was given a ticket. You sure?
Yeah.
Why can't juniors get tickets?
It says only if you are sophomore.
Because it's only if. You will be given a ticket only if you are a sophomore. If you're given a ticket, you were for sure a sophomore. So Gene was given a ticket, for sure a sophomore. Now George is a sophomore, so he gets a ticket. No! What if we ran out of tickets? What if I only had 5 tickets? I could have given them to the different kids, I could make sure that you get a ticket only if you're a sophomore. So I got 5 tickets, I say, you guys come grab them, but only if you're a sophomore. Then you get a ticket only if you're a sophomore, but just because you're a sophomore doesn't mean you get a ticket. That only if will come back to bite you 100 times. It's the one that always tricks you up. So, next one. The house will burn down if we don't get water. Okay, I tell you we did get some water.
The house might still burn down.
Right, we could have took a cup of water, thrown it on there, whoo, put that baby out. No. So just because you got some water doesn't mean you saved the house. But if you didn't get any water, for sure we lost the house. Okay, what if we didn't get some water? We for sure lost the house. There she goes. Okay, now another way that people confuse if then. If then is not the same thing as if we make it the case in this universe that blah 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 blah, then it would also be the case in this universe that blah 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 blah. Logic doesn't care about our universe. It exists independent of our universe. Couldn't care less how we change things in our universe. It's not what implications are talking about. So, if there are 100 husbands in America, then there is only one wife, is going to be a true statement. And initially you're going to hate that. Right? You're going to hate that initially. Because you're thinking in your head, if we make it the case that there were 100 husbands in America, then it would not be the case that there's only one wife in America. So you're going to hate this initially because you're going to think in terms of changing things in our system. And so we're going to introduce you to what it means for an implication to be vacuously true. When I'm looking at alpha implies beta, if the antecedent is false, the implication is always true, and it is called vacuously true. If the antecedent is false, the whole implication is true. It is called vacuously true. And that is because if you give me one false statement in any system, I can then prove anything you want. Everything becomes true if you allow one false statement. Let me give you an example. If you allow 1 to equal 0, I can prove anything you want. But the one I was going to do is prove to you I'm the Pope. You want to see that one, or you want me to prove something else? Any crazy thing you want? Prove I'm the Pope? Okay, I'm going to prove to you that I'm the Pope, using the fact that 1 equals 0. Now, the Pope and I are 2, right?
Yes.
Okay, so let's start with this. If I know 1 equals 0, add 1 to both sides. 1 plus 1 is equal to 0 plus 1, right? What's 1 plus 1? What's 0 plus 1? Now, the Pope and I are 2, Therefore, the Pope and I are one. Therefore, I am the Pope. If you allow 1 to equal 0, I can prove any stupid nonsense you want. It's called vacuously true. When the antecedent is false, the whole implication is always true. And you'll get used to this eventually.
Can you write out the truth table for the implication?
Yeah, so we're going to write out the truth table right now. So let's write out this truth table. And in writing out the truth table, another thing that's helpful for your intuition to keep in mind is that if alpha is not true, then it's false. Right?
Yeah.
What does it mean to not be true? It means false. If the statement's not true, then it's false. It's also helpful to keep in mind. So let's write out the truth table for an implication. So we got alpha here, we got beta here. Now we have alpha implies beta, our hardest truth table. Okay, we can have true, 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 false, false, true, false, false. We're going to set up the different scenarios. Alpha will once again be I'm holding a red marker, and beta will once again be I'm holding a piece of chalk. Let's set up each one and go through it. If I'm holding a red marker, then I'm holding a piece of chalk. Is that true? Now, you could be thinking, I could easily just set down the chalk and make it false. There is no change. There is no physics. I am the universe. This, me, in this state. No time, no space, no nothing. Just this. Logic doesn't care about our universe. Thank you. So, if I'm holding a red marker, then I'm holding a piece of chalk. True. If this were the whole universe, then that would always be the case. If I am all of existence with this. Okay. So that one's true. If I'm holding a red marker, then I'm holding a piece of chalk.
False.
Yeah. Liar. If I'm holding a red marker, then I'm holding a piece of chalk.
Vacuously true.
Now, here's where your intuition would say, is it false that if I'm holding a red marker, then I'm holding a piece of chalk? Is it false? Not really. It's not false. Well, if it's not false, what is it?
It's true.
It's true. That's what not false means. It's true. Prove me wrong. You can't. So it's true. It's what we call vacuously true. And the reason it's vacuously true is because 0 equals 1 implies any statement you want. If you put a false statement here, I can prove anything you want. The whole implication becomes true. It is true that if 0 equals 1, I'm the Pope. We went through that proof. It's also true that 0 equals 1, 0 equals 0. It's also true that 0 equals 1, I'm a 6-foot purple dragon. Right? Okay, so now finally, false, false. If I'm holding a red marker, then I'm holding a piece of chalk. Is it false? Not really. You can't call it false. And if it's not false, then it's true. And it's vacuously true. If the antecedent is false, then the whole implication is true. You're going to hate this. You're going to hate this for years. You're going to have to go through it like 3 times, and you're going to be like, that makes perfect sense. But after your first 2 times, it's still just, something feels off about it. You don't like it. Because you want to somehow introduce change into the system. Okay, so there's our truth table for an implication. We'll do that truth table a few times in the future because you'll mess it up again. It takes lots of practice. Okay. So there's implication. Converse. We call beta implies alpha the converse of alpha implies beta. So just terminology. When I talk about the converse of an implication, that just means swap it around. So let's just state the converse of some of these. If an animal is a man, then it is a human being. What's the converse of that?
The animal's a human being.
If it's a human being, then it's a man. The converse just states the implication in the opposite order. That's all the converse is. This is just terminology, so I can say, let's look at its converse down the road, and you know what I'm saying. Every man born in Indiana is an American citizen. So first off, let's think about the if alpha then beta form of this. What's it saying?
If a man was born in Indiana, then they are American.
If born in Indiana, then American, right?
Yes.
The converse would be if American, then born in Indiana. Right? Now notice, just because a statement is true doesn't mean its converse is true. So is it true that if an animal is a man, then it's a human being?
Yeah.
Yes, that's true. Is it true that if an animal is a human being, then it's a man?
Yes.
Well, in this case, they meant it the gendered way. No, it could have been a woman, is the way that they mean it here.
Okay.
Is it true that every man born in Indiana is an American citizen?
Yes.
Yes. Is it true that every American citizen is born in Indiana?
No.
No. So when you have an implication, its converse is not necessarily true. If the implication is true, that does not mean its converse is true. Its converse is its own statement, and you got to think about it. It could be true. It could also be false. If x minus y equals 3, then x is greater than y. Is that true?
Yes.
If x minus y equals 3, then x is greater than y. Is that true? Yeah. Because think about it as my money versus your money. If we take my money and we subtract all your money and we still have 3, then I must have had 3 more money than you. Using proper units. Okay, so that statement's true. Let's look at its converse. If x is greater than y, then x minus y equals 3. No. X could have been 10 and y could have been 1. Or whatever. Okay. If planets are green, they must have sunshine. Planets. If plants are green, they must have sunshine. We'll assume true for the sake of how core field works. Okay. What about the converse? If plants must have sunshine, then they're green?
No.
No.
Water.
Huh?
You could forget to water them.
Well, it's saying it must have sunshine to survive.
Right.
Oh, you're saying it wilts and dies.
Yeah.
Well, we won't call dead things a plant. I think what they had in mind is, no, there's perfectly fine having plants that aren't green, that survive and live. Okay. If 2 plus 4 equals 5, then 4 plus 7 equals 10. Is that true?
Yes.
Yeah, it's vacuously true. Let's look at its converse. If 4 plus 7 equals 10, then 2 plus 4 equals 5? Yes, once again, vacuously true. False implies false is true, because false implies anything is true. If I start the statement, if I'm a purple dragon, then you can plug in anything you want, the whole thing's going to be true. Right? Okay, so there's converse. Now let's get to contrapositive. The contrapositive, very different from the converse. Well, related, I should say very different. And we'll actually write out the contrapositive. This one's worth writing out. The contrapositive of alpha implies beta is not beta implies not alpha. So, what did we just barely do before the contrapositive? The converse. The converse just flips the implication arrow and makes it a beta implies alpha. Contrapositive negates both things and flips the implication arrow. So the contrapositive of alpha implies beta is not beta, not our end thing, implies not our start thing, not alpha. Make sense? So let's do the contrapositive of some of these. X equals 3 implies x squared equals 9. First off, is that true?
Yes.
If x equals 3, does x squared equal 9?
Yep.
Let's really quick look at its converse. Its converse would be x squared equals 9 implies x equals 3. Is that true?
No, not fully. It's x.
You just square root both sides. What's the square root of 9?
Plus or minus. It's plus or minus.
X could have also been negative 3, right? So we don't know, just because x squared equals 9, that x equals 3. X could have been negative 3, but for sure, if x equals 3, then x squared equals 9. So here's an example. The implication, true. Its converse, not true. Good? Now let's look at its contrapositive and determine if that's true or not. What's contrapositive? Remember, we're going to swap our alphas and betas and negate them.
Yep.
So we're going to say x squared is not equal to 9 implies x is not equal to 3. So I give you some magic x. The only thing I tell you about it is if you square it, you don't get 9.
Yes.
Could X have been 3? No. So this is still true. The contrapositive of a true implication will always be true. And the contrapositive of a false statement will always be false. Contrapositive gets you back where you started.
It's logically equivalent.
They're logically equivalent. So let's read through a couple more examples and then draw out the truth table. Okay. If two lines intersect, they are not parallel. Right? That's a true statement, right?
Yes.
Let's state its contrapositive. What's the negation of not parallel? Parallel. So it would be if, remember, you do not beta, then not alpha. So if two lines are parallel, then we need to write the negation of our antecedent.
They do not intersect.
Right? Our antecedent was two lines intersect. So the negation of that is then they do not intersect. Sorry. And is that true? Is it true that if two lines are parallel, then they do not intersect? Yes. Parallel lines don't intersect. So this one says if two lines intersect, then they're not parallel. This one says if two lines are parallel, they do not intersect. It turns out those two things say the exact same thing. They're the contrapositive of each other. So let's try out the truth table now. We did a couple examples. For not beta implies not alpha. Let's really quick to the side here, just really quick write out not alpha and not beta so that we can reference them. So we'll do it on the left side over here really quick. So first we'll do not alpha. Tell me what to write.
False.
Perfect. This is not beta.
False. False.
Perfect. Okay. So now we're saying not beta implies not alpha. Not beta implies not alpha. So false implies false is
True.
true. Vacuously true. False implies anything is true.
Yeah.
Let's try it the other way. True implies false is
False.
false. If I'm holding a red marker, then I'm holding If I'm holding a red marker, then I'm holding a piece of chalk.
Yeah.
False. True implies false is false. Okay. Oh, right. False implies true is true. False implies anything is vacuously true. And then finally, true implies true is true. And so notice what we got. We got true, false, true, true. Alpha implies beta, true, false, true, true. They were identical, so they're logically equivalent. Yeah. What time are we at?
10:32.
Okay. We'll take a quick break here, and then we'll come back and finish. So go ahead and go on break. All right. Let's jump back into this. Our last symbol now, the last of the 5 symbols we care about, is equivalence. We use this back and forth arrow to represent logical equivalence, or what we call if and only if statements. So 1,000 times in this class, you will see me write this word, IFF, is shorthand for if and only if. Now, when we say alpha if beta, what is that saying? Is that saying alpha implies beta or beta implies alpha?
Beta implies alpha.
Alpha if beta means beta implies alpha. I'll give you $20 if you mow the lawn means if you mow the lawn, then I'll give you $20. Right? So alpha if beta means beta implies alpha. The implication goes this way. So alpha if beta means beta implies alpha. Alpha only if beta, the implication goes this way.
Yep.
Right? Remember that they'll say the opposite of each other. So alpha only if beta is the same thing as alpha implies beta. So when I tell you alpha if and only if beta, I'm saying alpha if beta and alpha only if beta. So I'm saying beta implies alpha and alpha implies beta. I'm saying they both imply each other. That's what I mean when I say alpha if and only if beta. I'm saying alpha if beta, or sorry, here's alpha if beta and alpha only if beta. I'm saying alpha implies beta and beta implies alpha. I'm saying both those together. That's what we mean when we say alpha if and only if beta. That phrasing will show up in more rigorous textbooks 1,000 times. You will read alpha if and only if beta. Some statement if and only if some other statement. It means that they both imply each other. And the shorthand for that is alpha IFF beta. So I will write that a ton of times in proofs as we go throughout this course. Alpha if and only if beta. Hopefully not stressing it too much. Okay, so now what does this have to do with logical equivalence? Logical equivalence, we call two statements alpha and beta logically equivalent provided that alpha implies beta and beta implies alpha. That's what we mean when we say they're basically logically equivalent. We also call alpha if and only if beta a biconditional or an equivalence. I'll typically call them an equivalence in this class. Why is it called a biconditional? It's two conditional statements in one. It's saying alpha implies beta and beta implies alpha. Just terminology. Good so far? Notation, we write alpha if beta as alpha, back and forth arrow beta. So now let's do our truth table. So we're going to do alpha, we're going to do beta, we're going to do alpha implies beta, and then we're going to do beta implies alpha, and then we're going to do alpha implies beta, and beta implies alpha. Or alpha if and only if beta. We're going to and these two together. That's this. With me?
Yeah.
Let's fill out our beautiful truth table with my horribly drawn lines. Okay, so first case we could have true and false, right? Of course. True implies false is? False. If I'm holding a piece of chalk, then I'm holding a marker. Is that true?
False.
False. True implies false is false. Okay, let's look at false implies true.
True.
True, how do you know?
Fact.
Vacuously true. False antecedent, always a true implication. Now, and these two together. False and true is?
False.
False. Let's play again. Give me another combination.
False.
False and true. Okay, false implies true is?
True.
Vacuously true.
Oh.
False implies true is true.
If I'm a purple dragon, then Jupiter fits on my earlobe.
Yeah.
True statement. Okay. True implies false is?
False.
False. True and false is?
True. No,
It's
false.
false. Come on, guys.
True and false is false.
Okay, next one. What else can I write here?
True.
Okay, false. False implies false is?
True.
True. What?
Yeah.
You guys just gonna listen to him?
Fact is true.
Yeah, but this time false implies false is
Also true.
still true. False implies false is true. Doesn't matter which column I point at. Alright. And true and true is? When they're both the same?
Yeah.
Alright, and finally true. True implies true is? True implies true is? True and true is? Okay. So here's our table for alpha implies beta and beta implies alpha. Now there's a way easier way to construct this. Because if alpha implies beta and beta implies alpha, that means they're logically equivalent, or in other words, they have the same truth value. Is true the same as false? No. Is false the same as true? No. Is false the same as false?
Yes.
Yes. Is true the same as true?
Yes.
Yes. So that's how everyone actually constructs this truth table.
Right.
Is true the same as false? Is true logically equivalent to false? No. Is false logically equivalent to true? No. Is false logically equivalent to false? Yes. Is true logically equivalent to true? Yes. And that's the way we think about it. Do they have the same truth value? That's all this means, the back and forth arrow. They have the same truth value.
Okay, do that again.
Do that again. Alpha is true and beta is false. Do these have the same truth value? Is true the same as false? No. Is false the same as true? No. Is false the same as false? Yes. Is true the same as true? Yes. So when we're saying that two statements are logically equivalent, we mean that either they're both false or they're both true. In the same way.
Yep.
Okay, so that's what it means to be logically equivalent. Notation, we write alpha if and only if beta as the back and forth arrow. Okay, and there we go. We did our 5 special symbols. You know the 5 special symbols of propositional logic. Not too bad. Not, and, or, implies, and if and only if, or equivalence. That's it. Now, this is a precedence that we apply the operators in.
Like order of operations.
Like order of operations. Like if I would have written something like 4 plus 7 times 2 squared, you know, first we apply the squared, then we multiply the 7, then we add the 4.
Right.
And so, the correct way to do this would be 4 times 7 is 28 plus 4 is 32. A terrible way to do this would be 4 plus 7, let's see, that's 11, times 2 gives us 22, and square it, and we got 400 and whatever.
Yeah.
That's the dumb way to do it. So you need to understand the precedence. Same thing with these. Here's the order that you do it. First you not, then you and, then you or, then you do implies, then you do equivalence. Now, that seems like a lot to swallow, but this one, we often think about this as functioning the same way as our negative symbol, and we think about as functioning the same way as times, or we think about as functioning the same way as plus, implies, special, and then this one we think about as kind of functioning the same way as equals. So that's roughly how we think about it. Just an analogy to give you intuition, but nonetheless, that's the analogy that we use. Okay, so what does that mean? Here, let's read some mouthful of a statement. I got alpha implies beta is logically equivalent to not beta implies not alpha. How on earth do we break this thing down? So first, we would do the parentheses around. We apply the not to the beta and the not to the alpha first.
Which they already are,
Right? And then we would evaluate this piece together with this piece. And then we would do the logical equivalence all at the end.
Right.
So that is how you would add the parentheses to show you the precedence of how you do these. It's typically pretty intuitive how to do it. The only confusing one can be and versus or. And remembering your ands always come before your ors. So here's a more confusing one. Alpha or beta and not alpha. This one, you do the not first, but then you do your and before your or.
So it's alpha and beta and not alpha. Yeah.
It's alpha or beta and not alpha. Is how I would read it if I were forced to read it out loud. Let's just do an evaluation of some expression. So I don't know, I'll look at not, false, implies, true, is logically equivalent to false. Let's evaluate the thing. Okay? Just like doing algebra with numbers. What does not false equal?
True.
True. So we do the not first. So simplifying, we now have true implies true is logically equivalent to false. Let's see, true implies true is?
True.
True. So we got true is logically equivalent to false. Now true is logically equivalent to false is?
False.
False. So this whole expression evaluates to false. There's doing the algebra on it, so to speak. We call that Boolean algebra. And you'll have a section in a couple of weeks on Boolean algebra actually doing evaluations like this. Okay, make sense? I just like giving you all the logic and not just the Boolean algebra. So I go into the logic nice and deep. So there we go. We did propositional logic. Did I remember to restart my recording?
Yes, let's go.
Okay. We did propositional logic. So quick recap. The things that we care the most about. A proposition or a statement. What is that? A statement or a proposition is a sentence that is either true or false, but not both. So if I tell you something's a statement, it has to either be true or it has to either be false. One of those two things. Then we went over our common operators. Not and or implies an equivalence.
Yep.
And we proved a few theorems for you. We proved that not alpha and beta is the same thing as not alpha or not beta. Right? This is something that just follows from their definitions. Not alpha or beta is the same thing as not alpha and not beta.
Yep.
When you distribute a not over an and, it converts into an or. When you distribute a not over an or, it converts into an and. Let me make up some expression that would require us to do this. So let's look at not true and, or true or false implies true. We'll do this evaluation. Let's evaluate this thing. Okay? So first, let's distribute our not over our or. So distributing the not in, this is going to give me not true and not false implies true. Just distributed my or, right? Or sorry, distributed my not in there. Switch my or into an and. I was using this. Not alpha and beta is the same thing as not alpha or not beta. I took the not, applied it to this. I took the not and applied it to this. And it switched the or to an and. Right? Okay. Not true is false. And not false is true. Implies true. False and true is false. Implies true. False implies true is
True.
true. So this whole thing evaluates to true.
Accuracy true.
Yeah, the implication is accuracy true, but the whole thing evaluates to true. It's going to feel weird doing this type of algebra with Booleans, this Boolean algebra. Don't worry, that's a couple weeks down and we'll recover all this stuff before we go to it. Remember, we haven't started the book yet. I'm giving you a crash course on all the foundations for the book. That's what we're doing right now. You will not have to do anything like that on your homework. Your homework will just be writing sentences and getting comfortable with English. That's it. Okay. Now remember, going all the way back to our beginning, when I was asking you, is it a statement, is it not a statement? We came across this one. X plus 2 equals 5. Was that a statement?
No.
It wasn't? No. Remember, that was not a statement. Why was it not a statement?
Because X was undefined.
Yeah, because X here is a variable. If X happens to be 3, then it's true. But if X is 4, then it's false. And so we can't call it true and we can't call it false. It's in this weird limbo state. We can't decide what to do with it. So that is what we call a predicate. So that's our first example of a predicate. So we did propositional logic. That's the hard one. That's the bulk of it. Predicate logic will get a bit easier. And then logic with identity will be super easy.
Yeah.
So we're going to start on predicate logic. Your homework will have nothing to do with predicate logic. We've covered everything you need for your homework. So what is a predicate? A predicate is a proposition valued function of some number of variables. In other words, if you give a predicate its terms, then it spits out something that is true or false. So x plus 2 equals 5 is a predicate. Because when I plug in for x, then I get something that's either true or false. So it's not true or false by itself, but once I replace the variables with some term, then it does become true or false. So that is what predicate logic is, and what predicate logic is about is predicates. So we will start next week with predicates. Okay? Just give you a quick taste now for what they are. Good? Okay. So that is it for today. Any questions? Anything you want recorded?
So are we covering predicate and identity logic next week?
Yeah, we'll cover predicate, identity logic, and start the book next week.
Okay.
Okay, so we did that. So we'll, if you don't have any more questions, then we'll look at your guys' homework problem from last week. So, no more questions? Did you guys figure out your homework problem?
Yes.
Okay, so the
Nice.
thing is,